In this video, we're going to talk a little bit about Excel. And honestly, I'm not sure, at what place different people are when it comes to Excel as a skill set. Some people might be pretty familiar with the program already. Other people might not. So hopefully this isn't too basic, but I want to make sure that everyone at least has this kind of like fundamental understanding of Excel. Someone posed the question once in a forum or something that I was present at. They said, "What's the most commonly used engineering software?" And people were throwing out things like SolidWorks and Pro Engineer and different CAD programs and analysis packages, ANSYS, stuff like that. And at the end of the question, the respondents said, all of you are incorrect. Those are not the most popular engineering programs. The most popular, the most commonly used engineering program is Microsoft Excel, the simple, humble spreadsheet. And it's used so often for so many different reasons that I thought it was really important we at least go over Excel as an engineering tool. And it can be used. It's such a modular program. It's not like I can say Excel is always used by mechanical designers to do A, B, and C. There are hundreds of different ways that you could use Excel for organizing data, calculating equations, communicating ideas, so all kinds of different things. But let's just go through some of these discussion questions, and then at the end, I'll show you a few real world examples of how our team has used Excel. Discussion question, let's see, number 4A. Excel is designed to allow calculation of data sets, but it's also used very commonly, not only for processing data, but for organizing data. Why is this? So,
because, should I answer?
Yeah,
attempt to answer it. Because it has functions for looking for different numbers or phrases, and it could essentially scan the sheet for you. And sheets could be dozens or hundreds of rows and columns, and it could just do it for you instantly and give you an answer.
Right. Yeah, that's for sure one of the reasons. Another reason is because you can format it so that data is easy to see. Instead of, I don't know, you might receive a data set that's like a single column by 800 rows long, and it's really hard to see data formatted like that, just a single column that's like 800 rows long. So you could split this data up and have multiple columns, and different columns can be different colors, and you can make some of them bold and some of them not bold and some of them larger font, and it just makes it really easy to organize data. Data sets relative to each other, and just easier to see things. So it really just purely from like a practical, almost logistics standpoint, Excel can make just visualizing data a lot easier. And then, of course, like you said, it makes things, it makes it a lot easier to look up data as well. Okay, so 4B, pretend you need to determine the friction force of pulling an object across a surface. How could you use Excel to set up an equation and quickly change the variables to evaluate different materials and forces? So let's see, Raf, maybe I can give control to you, and we can kind of talk through. And do you want to try and set this up?
Okay.
All right.
So
let me give you mouse control here. Okay, so let's start by defining our equation. What's our equation for friction force?
Okay, so equals don't tell me, hold on. It was friction equals the coefficient of friction times force, and so normal force.
Right. Coefficient of force times normal force, right, equals the frictional force. And let's not even write equals right now. Let's just like write out the equation so it's there and easy for us to look at. Great. It's the friction force, right?
So there's a slight delay when I type. That's why I'm struggling here.
Just let's write the frictional force equals coefficient of friction times normal force. You can just abbreviate COF if you want.
It's kind of hard to do from here. It's like super small and there's a delay.
Okay, all right, I'll type.
Yeah.
All right, so we've got, I'm going to say frictional force equals coefficient of friction times normal force. So that's your equation. And we want to define our variables here. So frictional force is what we're trying to solve for. Our variables are going to be coefficient of friction and normal force. Okay. Now, coefficient of friction, it's usually something between 0 and 1. It can be more than 1, but usually it's between 0 and 1. Let's say it's just, I don't know, 0.25. Doesn't really matter. We're just doing an example. And then normal force, again, doesn't matter. Say 50 pounds, sure. So we've got our variables defined, coefficient of friction and normal force. Now, what does the equation look like right here that will allow us to solve for, in fact, why don't we just go down here and say frictional force. And what does our equation look like? How do we type that into Excel to solve for the frictional force?
Yeah, you just put equal and then select the cell 4B asterisk, which means multiplication, and this cell right underneath. You close the parentheses, you press enter.
There you go. Yep. So 12.5. Let's say this is pounds force, and then coefficient of friction is unitless. So this would also be 12.5 pounds of force. And what's so great about Excel is now that you have the equation in there, you can really easily just change your variables and your result changes, updates automatically. You know, what if it was 500 pounds instead of 50? Or maybe it's 1,273.687 pounds. Oh, put that in the wrong place. 1,200. Oh, okay, so this is interesting. Why didn't it work? 1,273.687. Oh, because I deleted the reference on accident. Alright, so anyway, we don't have to spend a long time on this, but it's super easy to just create equations in Excel and then update variables and your output changes automatically. So it's a quick and efficient way to look at you know, different variables and how they affect the outcome of your equation.
Sounds good.
All right, so let's see. Back to our discussion questions. Okay, imagine you and several other team members are reviewing a set of drawings and want to keep track of what drawings have been reviewed and which have not. Create an Excel document that enables you to do so. This is a simple exercise in creating a logically formatted Excel document with rows and columns to represent the parts to be reviewed and whether or not said parts have been reviewed. Don't overthink it. All right, well, let's just open up another sheet here. And I'm just going to kind of go through the process of how I would do this to give you an idea of another way that Excel can be used. So let's say that we have drawing number 1, drawing number 2, drawing number 3. And after you have a kind of a logical pattern like that, you can just select those and then pull this little plus sign down and it'll give you, you know, however far you drag it. So now we've got drawings 1 through 25. And we want to keep track of what drawings have been done and which ones have not been done. So we could type in here maybe drawing started. So we maybe I'm ready to start a new drawing, and even if drawing number 1 isn't finished yet, maybe someone has started it, and so I don't want to start a drawing that's already been started. So we have this indication of what drawings have been started, and then maybe we have another one, drawing maybe draft complete, and then maybe we have another column that's like draft approved, and then another column that's I don't know, drawing exported, because when you're working in SolidWorks, you have your drawing and you export it as a PDF typically whenever you send it out to someone. And then I usually kind of format this so it looks a little bit nicer. Put my header and row titles in bold, and then I might do like an underline over here, and then maybe I might put a comments at the end and drag that out so there's room to put some comments out there. And then as people are making these, you can come in and just put an X there. Okay, drawing started. Maybe this draft is complete, approved, but it's not exported yet. So you might have something like this. And then anyone on your team can come in and just see what's done and what's not, and get started on the next one. So that's a simple example of how Excel can be used just as kind of a organizational tool within a team.
Organizational / project management.
Yeah, exactly. Yeah. In fact, some people will use Excel as kind of a poor man's Gantt chart in order to track schedule. Yeah, it's not the best tool for that, but if it's something quick and dirty, you could even use it as kind of a Gantt chart to track schedule. There's just so many different ways you can use Excel. All right, so that's for C. For D, create user-defined variables and an equation in Excel to calculate the area of a circle. Ensure the area calculation, that is the output value of this calculation, can be quickly and easily changed by simply updating the value of the radius or diameter if you so choose. All right, so this is kind of similar to the first exercise, but we know that the area of a circle equals pi times r squared, radius squared. So if we come down here and we set up our variables, pi is not a variable, that's a constant. But why don't we write it out? And it's kind of interesting in Excel. Excel knows what pi is, but you have to put these parentheses for some reasons. You have to write out equals pi, open parenthesis, close parenthesis, and that's how you tell Excel that you want to use pi. So 3.14, etc., etc. And then we'll say we have our radius in here. I don't know, we'll say 1 for now. And then down here we'll have circle area. And now this is where we create our equation. So our equation is going to be, what is it, Raf? Equals?
You're going to select the same thing as before, but we're going to square it.
Okay, so pi times, and then we'll put an open parentheses here. There are a couple ways you could do it, right? You could do that. You could b5 times b5. That's r squared. Or another way you could do it is b5 and then the little caret symbol and 2. That's the same thing, b5 squared. Okay, so since our radius is just 1, it's 1 squared is 1 times pi is same thing. But if our radius is 2, now that changes our circle area to 12.5 and so on and so forth. 2.5, we get 19.6, etc., etc. And then going back here, we're going to take it a step further. Add an equation that calculates the shear stress of a member with a circular cross-section. And here we have the equation for what the shear stress of a beam with a circular cross-section is. And this is something that, in fact, I can maybe show you a spreadsheet that I've put together over the years that has several common equations in it. Yeah, we'll take a look at that in a second. But let's see. Shear stress equals 4V over 3A, where in the equations lesson we go over this, but V is just the variable used for shear force. So the force that's applied to a member in order to create that, produce that shear stress. So same thing that we did before, right? We define our variables. Shear force, which is V, doesn't matter, we'll say it's 10. And then area, we can just take from above. And so we can come down here now and say shear stress, and we'll go equals 4V divided by 3A. So say open parentheses 4 times V, which is B14, and close parentheses divided by, open parentheses again, 3 times our area, which we've already calculated up here, and then close parentheses, and 0.679, that's our shear stress, is probably PSI if we're working in inches.
Makes sense.
Makes sense? Okay.
Yeah.
So let me show you. This spreadsheet that I put together over the years that has a lot of different equations in it and has just been really useful. Okay, here's the spreadsheet, and you can see on the bottom there several different tabs. We've got deflection of, well, it says circle deflection, but that just means deflection of a cantilever beam that has a circular cross section. So you can see right here there's this circle that represents the cross section. We've got a cantilever beam here that's fixed on one side and a load is applied to the other side. Next one is tube deflection, which is really the same thing, but it just accounts for a hollow interior of that circular cross section. And then next one is rectangular beam deflection. We've got one for buckling force in here, circular buckling force and rectangular buckling force. We've got shear stress of a circle, shear stress of a square. And then on the right side of all these, I've got some common material plastics or common materials with their associated material properties. Like we've got the modulus of elasticity listed here, the yield strength, the ultimate strength. And so what I've done here is I've defined some input variables, which are my yellow cells here. And if we, imagine this red rectangle here, this is a bolt or a pin or something, and we're loading it up as shown with the arrows, right? So we're creating a shear stress right here in the middle. And I'm saying that if my, this is a rectangular example, shear stress for a square. So we're saying if we have a base of, 5 millimeters and a height of 10 millimeters, and we're applying 500 newtons of force, and there's just a single member, meaning it's in single shear, not double shear, then we get these output values down here. Max shear stress, 1.5. Max shear stress divided by number of members is also 1.5 since it's in single shear. And then down here, again, this is covered in the equations lesson, but our shear yield stress, rough rule of thumb, is just half of your yield stress. So what I've done here is I've just linked to this yield stress here, and this yield stress just I'm pulling from my list over here, and so we see that we've got a factor of safety of 7.17, and it will not fail. Now I've done a little bit more some conditional formatting in this spreadsheet so that if it does fail, it shows me a big bright red symbol. So let's say this is, instead of 500 newtons, it's 5,000 newtons. And now it changes to, yep, it will fail. The factor of safety is less than 1. And my shear yield stress is less than the actual, let's see, the shear yield stress is less than the calculated stress that we see in this member. So there's just another example of how you can put together, a variety of spreadsheets that quickly allow you to calculate things. So here's deflection of a beam, right? I could tell it how long my length is from the fixed point to where the load is applied. I could tell it what the diameter of my rod is. I can tell it what material it is. Here's the modulus, and then it tells me what's the bending stress. Is it going to plastically deform, and what's the deflection?
Excuse me, how did you get to this screen? Did you change the tab?
Yeah, these tabs down here on the bottom.
Let me see.
You see it? Yeah.
Oh, okay, I was zoomed in. I see it now.
Oh, okay.
Great.
Yeah. All right. So once you set up an equation like this, it's so easy to reuse it, and these are some common ones. But yeah, any other questions there, Raf?
How often does a designer use a sheet like this with equations for a mechanical design?
Not super often, but often enough that it's really handy to have something like this put together. I might use this probably not even once a month. Maybe, I don't know, 8 or 10 times per year, maybe something like that.
How do you know which kind of projects require a sheet like this versus other projects that you can just do the hand calculation and you're finished?
You don't really know at the beginning of a project. I mean, once you get into the project and you determine that, okay, I'm going to have this feature that looks like this. Okay, that is essentially a cantilever beam, and I want to understand what its deflection is going to be when I put this much load on it. So it's not like at the beginning of a project you would determine, okay, I'm going to need this equation, that equation, and that equation. You kind of have to get into the project before you know what has to be solved. And then as far as using this versus just hand calculations, I would never do a hand calculation of bending stress or deflection, because this it's so much faster to just open up this spreadsheet that I've created over the years, and I know the equation's already in there for me. All I have to do is plug in a few values and it spits out all these answers. So at this point, me personally, I would never do a hand calculation manually for deflection or bending stress, because this spreadsheet is quicker and more efficient and just does the work for me. Does that answer your question?
Another? Yeah, go ahead.
Does that answer your question?
Yeah, it does. Thank you.
Okay.
So what's another example for that Excel is used for?
Okay, so let's look at a few other sheets that we've got here. So this one, we wanted to evaluate various metals and the corresponding material properties. So in column B, we have various grades of steel and stainless steel. And then in the next columns, we've got like modulus of elasticity and yield strength. And then we've got a cost row. So obviously this is not like cleanly formatted or anything, but sometimes it doesn't need to be. You're just looking for a quick and easy way to organize some data and look at it. So this table right here allows us to pretty quickly look at how different modulus and yield strengths compare between different grades of steel.
Great.
Okay. Next one here. Oh, this is the one that we just did. So I'm just gonna cancel out of that one. This one we had a dial indicator here, and we were using this dial indicator to measure. I think we were actually measuring tissue, some biologic tissue, and the tissue was different thicknesses. But one of the constraints in our project was when we measured this, we had to ensure that the same amount of pressure was being placed on this tissue when it was measured. And we don't really need to get into the specifics of why we were doing what we were doing, but we used a spreadsheet like this to measure corresponding force values when we displaced that dial indicator. So when we displaced the dial indicator by 0.1 inches, it produced 45.5 grams of force. And we set it up on a mill. We put the dial indicator into the chuck of a mill, and then we had just a really accurate scientific scale underneath it, and just pushed on the scale and took the force readings. And we put together a little chart, and then from that data, we were able to determine what the pressure would be on this piece of tissue, because we knew the diameter of this anvil, the plunger down here, and that diameter is what was directly contacting these pieces of tissue. So calculated the pressure, and then we had a really good understanding for what pressure would be placed on tissue based on how much displacement there was. And then we could go kind of back ourselves in and correct for the displacement to make sure that the correct amount of pressure was being placed on each of these samples. So again, it's probably confusing, and we're not going to get into the details of why, but suffice to say that we were able to use a spreadsheet to first of all record data, and then use that data to make some calculations that were really useful in the rest of the project.
So in the signature program, will we do something like this for one of our projects?
I imagine we will, yeah.
Okay.
One of the goals of the signature program is to be kind of fluid. We don't want to be too regimented, but we certainly will have some high-level objectives, and I'm sure that there will be some Excel use in there.
Okay. One of the take-home points for me that I didn't know is that you can actually insert photos into the Excel sheet. And what I imagine this does is it reminds you of the project and where the variables come from. So if you can look at a visual, it helps you think of it, right?
Absolutely. Yeah, we do this pretty commonly, actually. And then to be even more thorough, you can put little call-outs in there and say, this is the dial indicator, or whatever you need to communicate to someone. Because sometimes you'll work on a project and the project will end, and then a year later, a customer comes back and says, hey, remember that test we did? What was the result, and why did we do it this way? So if you can open up your spreadsheet and you have some notes in here, it just makes it a lot easier to remember things and be clear.
Great.
All right, I think there's one more in here. Yeah. All right, so this one, there's a project, and I've deleted all the concepts to, maintain confidentiality. But suffice to say, we had several different concepts for a particular project, and then what we wanted to do was evaluate all of those concepts based on some numerical value that would lead to like an objective reason for choosing to proceed with one concept over the other. And so what we did was listed out all the concepts, and then in the ensuing columns, we put down the criteria that were important to the success of this project. And so one of them was robustness. Another one was simplicity or cost. How much does it cost to manufacture this? We had range of adjustability, and then ease of use. And then we went through and we applied a numerical value to each of these, for each of these columns and for each of the concepts. So it looks like what we used was a scale from 1 to 5, 1 being the worst and 5 being the best. So apparently concept 1, we gave it a 4 for robustness, which means, yeah, it's pretty robust. 5 would be the maximum robustness, but 4 is pretty good. Simplicity cost 4, so pretty good cost-wise. It wouldn't be too expensive. Range of adjustability 5, so this gave us all the adjustability we would ever need. And then ease of use 2, well, that's kind of low, so it ranks pretty well in these three things, but ease of use ranked a little bit lower. And so then we had a total which just sums all those values, total of 15. And we did the same thing going down here. We can see that we've got 15, 16, 15, 12, 14, 13, 12, 12, 18 different values. And so at the end of the day, we can come in and say, okay, well, it looks like concept number 9 has the best score, a score of 18, and that's the one that we should strongly consider pursuing because it appears to meet all of our objectives better than any of the other options. Make sense?
Yep, makes sense.
Okay. All right. So there are several different examples of how you can use Excel as a mechanical designer.
Sounds good.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.